Okay, so for number 6, again, we're going to determine whether we're in equilibrium or non-equilibrium. And so we read that it is still speeding up. So we know that it's not equilibrium, which means we're going to have arrows. Some arrows are going to be longer than other arrows. And we want to do it for the skydiver. And so we're going to do a schema. And so we've got the skydiver. And we know that we have the Earth. And we're probably pretty sure that there's going to be another force. And if you look on the giant packet that I gave you, it talks about there's a list of contact forces. And one of those contact forces is being, I can't remember exactly the way it phrases it, but there's something called drag, and that is due to the air. So anytime you're moving through a fluid, and air is definitely a fluid, you will have drag. So the interactions that we're going to have is Earth and skydiver, we know is weight. And then we just said that skydiver and air is drag. And we'll draw a boundary around the skydiver. And we will represent the skydiver with our dot. This is our free particle. We're assuming that both of the skydivers, there are 2 of them, all of their mass is concentrated in this single dot. And the weight always acts straight down. And the drag, it's like friction. It opposes the direction of motion. So if my motion is down, the force or interaction due to drag is going to be up. And we know that it has to be shorter than the weight because we have to have non-equilibrium. So I'm just going to write this out. It's shorter so that we can have this speeding up. Not equilibrium. These are not the same length, so I'm not going to put on congruency marks, and there are no horizontal forces. When I look at it, I've got 2 forces, and I see that there are 2 interactions that are breaking the boundary. Okay, next one. Draw a force diagram for a skydiver who is descending at constant velocity. So we know that this is going to be equilibrium. And as before with the skater, we're going to assume that the parachute is part of the person. So anything that the person is physically attached to is the system. And so we're going to have our skydiver. And we're going to have the Earth. And we're going to have the air. So we've got the same schema as before. I've got weight and I've got drag. What's different in this case, all right, so I've got the weight going down. What is different in this case is that because I'm in equilibrium, I know that the drag going up is the same length as the weight going down. I now have a pair of forces, so 2 forces that are the same length, and so I'm going to put congruency marks on them. Okay, draw a force diagram for cork floating in water. Label the forces and use equality marks for pairs of forces that have the same value. So I've got a cork, and the cork is touching the water. Because it's floating, we're going to assume the horizontal or the vertical velocity is 0. So this is going to be equilibrium, and we're going to say V vertical is equal to 0. If you want to put the water is touching the dish, and then we also have the Earth. So water dish, water cork, cork Earth. So that is weight. Now, you might want to put on that between the cork and the water, we have the perpendicular force. That perpendicular force is only true for solid objects. And instead, this is a buoyant force. Okay, or the force of buoyancy. We're going to put a boundary. So we're looking at the cork. And we've got the weight down. And going up, we have buoyant force. And they are the same length because the cork is not moving vertically. And so I've got a pair of forces that are the same length because this is in equilibrium. Our observation is that the velocity is 0, and so the conditions are the force of equal length. Okay, last one. Draw a force diagram for an airplane in straight and level flight. Label the forces and use equality marks for pairs of forces that have the same value. Now the one thing, assume constant velocity. Okay, so we know for this one, assume constant velocity. All right, so level flight means that vertical velocity is equal to 0. And so that means I'm equilibrium in vertical direction. And then constant velocity means horizontal equilibrium. And the velocity equals a constant. So in both directions, I'm going to have pairs of forces that are equal to each other. So let's do a schema. So we've got the plane. We've got the Earth. And the only other thing working on this is the air. So plane and Earth, we have weight. And you may remember from physical science that the plane actually has 3 interactions with the air. One of them is lift, and this is up. Another one is drag, and that slows it down. And then the last one is something called thrust. So all 3 of those are air interactions. So we've got weight going down. And because we are in vertical equilibrium, that means my lift going up, I've got a pair of forces that have to be the same length. So this is vertical equilibrium. And then I'm going to do this in a different color. I know that I have thrust going forward. I'm going to draw it a different length because the length of the thrust or the size of the thrust is not necessarily the size of the weight or the lift. But I know that thrust is equal to my drag. I'm going to do 2 congruency marks. I know that drag is equal to thrust because I have horizontal equilibrium. So kind of the key words that tipped me off was that this was constant velocity and the vertical was level flight. Okay, the last problem of sorting you will do later.